So, hi everyone, my name is Ratnesh and I started my journey with recent technology. After that, I worked in HCL technology. At present, I am working as in C Geo Platforms Limited, and my major work included C++ and telecom domain. Apart from it, I have worked little on Python and very less on Java. You can follow me on LinkedIn or Twitter with my handle social Ratnesh. So let's begin with the Lambda. Lambda originates from the mathematical
Ratnesh, sorry to interrupt. We are not able to see your screen presenting.
Yes, I presented it. Wait. So the lambda originates from the lambda calculus, and it was in 1930 that it started. What is lambda calculus? It originated from the anonymous functions. Anonymous functions are used to perform some operations without naming the function any name. Most of the programming languages implement anonymous functions with the name lambda. So lambda was basically lambda functions are used to implement anonymous functions, and they implement it with the help of an object which is a function object in C++. It was introduced in C++11 and then evolved throughout the different versions of C++. Where we do we need lambda? If you know Python, then there is a way that we can write nested functions, like a function inside another function. There is no way in C++ to do that with a named function. So lambda might be useful there. Many times we need a helpful function, like if we have a function 1 to perform some action, and we create another function 2 as a helper function. Only function 1 can use function 2, but if we use named function, then function 2 can be independent and anyone can call function 2 from any scope also, if we do not restrict it. If that same thing can be performed using lambda inside that function 1, so function 2 can be made as a lambda inside function 1, and then it can act as an inner function. So that way we can achieve the nested function or inner function in lambda in C++. It acts as a local function. Also, it has uses in standard algorithm that when as a predicate, we directly instead of writing a named function, we can directly use inline functions, and that can act as our predicate. Drawbacks of lambda. If what are the drawbacks? That it has some drawbacks, like if we write a structure or class, we can use abstraction to hide private members. We can and our members and only member functions have access to it. While in case of lambda, if we want to capture anything or use local variables, we first have to define it and then use it. So we are not able to hide those information in case of lambda, and that's its drawback. So first thing is that lambda syntax. In its simplest form, lambda syntax has a capture list and a body. Capture list is within two brackets and body is like a normal function body, named function body. So the first was it has capture parameter list like a named function, specifications and requires optional, and then a body. Specifications are SSIRs, and then like those mutable constant for things, exceptions, and other like return types, that trailing return type in C++11, you know. It has evolved with C++, and in C++14, C++20, it has also templated parameters. And those templated parameters can be constrained using requires and rest are the same. So if we include all these things in one way, it has a capture template parameters list requires to constrain on the template types parameters like a named function and then specifications and then return type, trailing return type and its body. Details of lambda. Though, so the part of lambda are capture parameters, body, specification, template parameters, and requires. So what are captures? Capture are used with square brackets. These square brackets are also called lambda introducer. It's called lambda introducer because every lambda starts with these square brackets. It can be used to capture variables, local variables with auto duration, auto static storage duration, and can be used those we can use those variables inside the lambda. It has parameter list. Parameter list is like normal parameters, name function parameter list to pass arguments when we calling the lambda or invoking the lambda. This parameter list is optional in case we don't have anything to pass to lambda, but it is mandatory even if we don't have to pass anything, but we want to use as specifiers. Since C++23, it's completely optional if we don't need any parameters. Body. Body of lambda is same as like a named function body. Whatever operation you need to perform, whatever action you need to statement you want to execute inside the body, you can execute it. And specifications. It does. These are specifiers, exceptions or attribute and trailing return type. Specifiers, specifications. So we can use the things that we use with named function. We can use here also. Template parameters. Template parameters are like template functions, just like we use in template functions. We can use that in template in lambda, and that is available since C++20. Requires is used to constrain the template types. Like if we have a type name t, and that t we want to only to be integral, then we can use require constraint on type, and that is available also since C++20. One thing is that whatever we capture in this capture list becomes available in the scope of the lambda body. So till the time we do not capture it, it is not available in the scope. That's why we need the capture list. And the variables which are with auto storage duration can be captured. Variables which do not have auto storage duration, like global, static, thread local, they don't need to be captured. They can be can be used inside the lambda, even if we do not capture it. So let's first see the capture list, because all the other things like parameters and body are like normal functions, just like named function we see. Most important thing in the lambda is capture list. That how capture list works in lambda, how we can use it. So first let's see the capture list. If we have an empty bracket, it means that we do not capture anything from the local scope. We do not capture anything from the local scope. If we want everything in the local scope to be captured by reference, we use the reference inside the bracket. It will capture all the things, all variables with auto storage duration with by reference. If we want to capture those variables auto storage duration by value, we use equal to. If we do not want to capture all the variables and want to capture only a few of them, we can specify them in the capture list, their name in capture list. and then we can capture y value or y reference. We can capture y reference or y reference in the capture list if we want to capture a few variable y value. Just name them. If you want to capture y reference, just put a reference before their name. Now, if next is reference and capture list. If we want to capture all variable by reference, but a few y value, we can use this. So first we put the implicit capture by reference and then the capture list. The capture list in this case cannot hold by reference. Any name, if we mention, if we can implicitly capture by reference and then we list a capture list and we put any name by reference, this will result into a compilation error. Similarly, if we want to capture implicitly by value but a few variables by reference, we can use equal to and then a capture list. That capture list cannot have capture by value. It will result in error. So next details about capture list, that variables which do not have auto storage duration cannot be captured. Like global, static, thread local, they don't need to be captured. They can be used directly. Variables with constant expression like a integer which is a constructor initialized, that also no need to be captured. It can be used without capturing it. So next is that if we capture all the things by reference, so the lambda may be optimized just to contain a pointer to the step frame, and anything that all the things that are available before that lambda will be just pointed by that pointer, and it may optimize it. That is up to the compiler. Next thing is lambda and lifetime. So all the things that we capture inside a lambda, when we invoking the lambda, should be present, should be its scope when we call that lambda. Anything that is captured like by reference, or if we are capturing a pointer, and at the time of lambda invocation it goes out of scope, the behavior might be undefined. So the best thing is to copy by value always. If we copy by value, we will not fall into the pitfall of undefined behavior. So, and next is name space name. So variables which are at the name escape lower, name is space scope, or like at global scope, they don't need to be captured. Next is lambda and this. So if we have lambda inside a member function and we want to use the members of this class inside that lambda, we need to capture this. And if we capture by value or this, it will capture this pointer. And since it captures this pointer, it does not copy those members, but it has only a pointer to those members. So make sure that when the lambda is invoked, that pointer is in its scope. If it goes out of scope, those members will not be accessible, resulting in undefined behavior. So till C++14, we don't have to a way to capture this by value. Since in C++14 we can do it there is another way. Since C++17 we directly can capture this pointer by value using this by dereferencing. Mutable lambda. So whenever we capture anything, by default, we cannot change that variable inside the lambda body. If we want to modify that variable inside the lambda body, we need to use a mutable specifier. How and why we will see later. Next is type of lambda. So we are saying that this lambda is an enormous function. So what would be its type? What would be the type of the lambda? The lambda has no type, and that is because so that the compiler can optimize it in its own way. If we need the type, we can use decal type on the function object. That is the object using which we access the lambda or has the access to lambda. Similarly, this function object which is created by the lambda can be wrapped in strict function object or using it in a function pointer in case it does not capture anything. Next is lambda call and return. So in case of its minimal expression, the lambda has only a simple capture list and body. So how does it finds out that what is the return type of the lambda? There are two ways. First is that it reduces based on the return what we are returning from the lambda, and second one is that we can specify ourselves by the trailing return type. If we have multiple return statement inside the lambda body, we need to specify it explicitly using the trailing return type. Now lambda implementation. How lambda is implemented? We say that we don't have any name to the lambda. We are using enormous function which does not have a name. But how does it implemented? Lambda is implemented using a class, and that class is called the closure class. So what it has that just like a capture has all the things that we capture become the member of that class, and then the parameter list and the function body becomes the part of the function call operator inside that class. It defines the function call operator and it becomes part of that function call. By default, that function call operator is const until we specify the mutable for it. So that class using which the lambda is implemented is called closure class, and the object means the name we provide to create the object is called closure object. So here I have a simple lambda which is capturing a local variable, integer variable. It has a parameter list and then it has a body where it multiply the multiplier to the parameter list, and here I am calling that lambda. If I had to do the same thing by writing myself, I will do like this, that the multiplier, this multiplier will become member of this class, and to initiate it, it will have a constructor, and the parameter list and the function body will become part of the function call operator, that is operator parenthesis parenthesis. It has a parameter list and the same function body. By default, it is constant. If we specify mutable, this will not become constant anymore. So this is how we can implement the same behavior as the lambda. Next is this lambda implementation. This is generated using the C++ inside. So all the slides in this PPT has a link to compiler explorer and CPP inside. So you can go and watch yourself. Also, you can do things that you want to. If you want to learn something that how behavior changes, you can edit this code and check yourself also. So the same lambda implementation using C++ inside, that we have multiplier, parameter list, and the function body. It defines first this function multiplier. It makes it as a private member of this class. Second one is that it defines a constructor to initialize this member, and then the parameter list and the function body becomes part of the function call operator. And by default, this is constant member function. And after that, it generates a member of this class, a object of this class, and that is the function object. This lambda, this is the function object. So first thing that we are going to say in the C+ lambda in C++11. It has a capture list, parameter list, body, specifiers, and capture list can be any variable presented in the local scope with auto storage duration. Parameter list is like a normal function call. Body is also like a normal function call. Specifier could be mutable or any trailing return type. There are some drawbacks which we will discuss later of this about this lambda. What are this C++11 lambda? So first see that how different things work in this case in C++11. The most important thing, as I said, was the capture list, and this makes the lambda different across the same version. So if we have a capture list here and without parameter, like I said that lambda is in simplest part has only a capture list and a body. It has a capture list where it captures the local variable and has a body. So this becomes the part of the body simply, and the capture list which has capturing by value becomes a part of the member function and constructor. If we increment this value after capturing it, it will have no effect because on this inside this lambda, because the value is already initialized, and since this is by value capture, it will not impact inside the lambda body. Lambda without capture. If we do not capture anything, then the lambda becomes equivalent to or compatible with the function pointer. So if you do not have anything in capture, then this will not have any member, and this also does not need any constructor. It should have only a function call operator, and the way it becomes compatible with the function pointer is this. It uses a function pointer like this here return type is int and this function pointer and then an int, and this uses this return type of function pointer and implements the way it will be compatible with the function pointer. So why do we need this? When we can need this? Suppose we have a CppI which takes a function pointer as a argument and we are calling it from C++. So we can write our lambda and then without capture list, and this will become compatible with the function pointer and we can pass that to the CppI. Next is mutable lambda. If we make the lambda mutable, the only difference comes in the function call operator. Here I have strike through the constant, means this will be dismissed from the function call operator and it will not be a constant anymore. And since this member function is not constant anymore, we can modify the variable member inside this function body. So the mutable level has only this difference. So if we have the mutable, this makes the lambda stateful. Stateful means we can modify the value or behavior of the captures list. Also, though we can specify multiple specifiers if they do not contradict with one another. So mutable and no except had different meaning, and so we can use multiple specifier in this lambda. And here I'm demonstrating that. So anything that we specify in the specifier, it becomes part of the function body of the function call operator. Since mutable is specified, const is not present, and we specified no except, so this becomes no except. Next is of the use of global and static. Since the global and static or any other variables which are not captured, they should be used very carefully inside the lambda. Because if they have changed during the lambda definition or when we define the lambda and when we calling the lambda, the result might be different than we expect here, than we predict here. So like in this case, if we predict the output of this lambda at the in general like a newby, here we have a global value of 10, local value of 20, static value of 30. This is captured by value inside the lambda 1, and here 10, 20 and 30, 10, 20, 30 and parameter list is presented during the function call. So here lambda 1, this will not be captured, is 40, 10, 20, 30. So it will be 100 according, like if we see this result here only, not at the time of the invoking the lambda. And in this case is by reference is here. But if we see this output, like if I compile this in compiler explorer, the output might be different than we thought. 370. So how these things happens? We have a global, static, local value and param. Parameter and local value will not change since this is captured by value and this is passed during the call. But for global value and static value, it does not captures by value at the time of we are defining lambda. What it does that it has its address of the global value, address of the static value, and when we invoke the lambda, it will read the value present at these addresses. So here we can see that the global has changed inside the main and static has changed before this invoking this lambda. So this new value will be considered at the time of invoking this lambda. Second thing is that inside the lambda 2, we have captured by reference. So the local value has changed also before invoking this lambda. So in the lambda 2, this new value 50 will be considered for the LVAL and not this 20. In lambda 1, we have captured it by value. So it will be captured, the same value will be captured. There is no issue in that. Another thing is that any variable with auto storage duration, any variable which is defined after the lambda, even if we capture by reference, it is not captured. So this variable which is defined after this lambda definition, it will not be captured in any case. Either we capture by value or we capture by reference. So this new value when we call fun and then here we have invoked the lambda 1. So the lambda 1 for the lambda 1 it will have global value that is 60, static value that is 50, 60, 50, 110, L value that is 20, so 130 and param is 40, so 170. For this 170 and for lambda 2 the difference is of LVL, so it has 30 difference, so this will be 200 and so 170 and 200 and the result will be 370. So the whole objective of this slide was to demonstrate that if we are using those values which are not captured inside the lambda or can be used without capturing, you should be careful with those values. So what some key points of are the summary of the C++ level lambda. That we can use as inline function. It is more readable, more expressive, and more efficient. More efficient that it has better performance than normal named function. And I have checked it on CPP benchmark also. On Quickbench. Previously, I have checked. I don't know. I don't have link for that. You can do it yourself. It is better alternative than the bind because bind is heavy. It is lightweight than bind, and it is then in that case it is better alternative. Since C lambda was introduced in C++11, it missed many things that were still present in C++11. Like one of the thing is that we have templated function since the beginning of C++. But if you want to make the lambda body templated, there is no way. Also that we can, although capture the local variables, there is no way that we can capture an expression. Like if I want to capture result of a return value of a function, I cannot do that directly in the capture. First, I will need to create a variable and then I will need to capture it. I cannot directly capture it. Another thing is that Lambda is not default constructor. There is no default constructor for the lambda. So we cannot create like we have a type like int well. So we cannot do decal type of lambda and then create a object of it because it does not have the default constructor. And this causes problem when we want to use it inside these containers. So we'll see how the lambda evolves and we can use it later. So as we know that C++14 had fulfilled those drawbacks of C++11, it has also major changes for lambda. So now let's see how lambda has changed in C++14. So the major thing that C++14 has changed is the capture list, and that it has made to capture any expression. The capture C++14 capture in case of lambda is called generalized lambda capture or init capture. It means that just like we define a variable with an expression, we can define a new name in the capture list with an expression inside the C++14 lambda. And since the expression is allowed, we can capture any return value from any function. We can capture or like move the objects inside the closure using std move. Like there is no way to move a unique pointer in case of C++11, but we can use std move in C++14 to move a unique pointer inside the lambda. Now, one thing to note here is that when we define this new name, data member, and the expression, this left side is in the scope of the lambda, and the right side is any expression from the outer scope of the lambda, like in where the lambda is being defined. Also, the C++ has offered the generic lambda. Generic lambda in the sense that we can use auto in the parameter list. And that is very beneficial because auto in case of named function were only introduced in C++ in parameter list were introduced in C++20, not even in C++17. So if you need a function where you want to use generic parameters and you are not using later version of like C++20, then in C++14 you can use it using a lambda. How C++14 lambda define this we will see later. And since we can use auto, we can also this also allowed us to implement variadic lambda, means the lambda taking variadic number of arguments. Another thing was that we know that we can use default value in C++, but in C++11 lambda, we cannot use default value of a parameter. In C++14, we can do that. So the best benefit of the C++14 lambda is that it has totally eliminated the use of std-bind. Like in C++11, the drawbacks, if you want to come over the drawbacks, the only way was to use std-bind or write your own class. But this eliminates the use of std-bind because of the generalized lambda capture. So the first thing we will see is that init capture in C++14 lambda. So here I have a unique pointer and I am moving this inside the lambda closure and then using that unique pointer. It is implemented in the same way. So this variable, or you can say name, which I has defined inside the capture, becomes part of the lambda member, and there is way a constructor is written to initialize it. It is not present outside the uh, scope of the lambda. If you see this name are same, you can use the same name. The left one will be in the scope of the lambda, the outer one is from the same scope where the lambda is defined and before the lambda is defined. So this up UP is this one, and this UP unique pointer is the one inside defined inside the lambda. Rest all is the same. The only thing is that it defines this unique pointer inside it. If you name it differently, you can name it same. Second thing is that you can write any expression, like here I am using a function object. Here I am using a function object to perform addition of two directly of 5 and 3, and that expression is being captured with a new name well, and then can be used inside the lambda. So the same will take place here also, that it defines a new name with that variable, and then it uses a capture a constructor to initialize it. It defines the lambda or function object, and then it construct it using that expression. Now the generic lambda. This is very interesting in C++ coding. So we know that in C++ to achieve generic way is template, and generic lambda is also implemented using the same, that is using the template. So what happens that in case of C++ 14 generic lambda, everything that is generic becomes a template thing. So here that lambda function body, which is a generic, becomes a template function inside the lambda. And similarly, the constructor is also templated. Sorry, this does not have capture, this does not have remember this invoke function pointer is also becomes the generic using the template. So here we can see that I have written a generic lambda, and I am able to call it with a integer, a double, and a string, and it gives me the output as expected. So this is benefit of the generic lambda, writing generic lambda. Another thing is variadic lambda. I am going to open this in C++ inside, sorry, compiler explorer. So here you can see.
Hi Ratnesh, your compiler explorer screen is not visible, I think.
Okay, because I had presented.
At least not visible to me. I'm not sure about others.
Okay. Wait. Now,
Yeah, it's visible now.
yes.
Thanks. Yes.
Sorry. So if people are also missed this example, right?
Yeah, we missed this one. Yeah.
Yes. Okay, no problem. I will repeat it in last. So here we have generic lambda. So here what I am doing, that I can call a variadic lambda. I can call this variadic lambda with any number of arguments. So I have written a lambda which calls a variadic function which prints, just display this using if functions. So what it does, that this variadic lambda takes variadic number of arguments and then forwards this to a variadic template. This variadic template calls the function to display these values of this member of this type. And then if you know these things, ignore this thing if you just don't know how to process the variadic arguments inside the template function. Okay, you just concentrate on this part. You just concentrate on this part, that how we can capture variadic arguments in lambda. So here we can capture in parameter pack, and that we can use the parameter pack inside the lambda body to call any other variadic function, or we can process the parameter pack inside the lambda body if you know how to unpack the parameter pack. So the generic lambda also allows the variadic lambda. In C++11, there is no way that we can do this. Next is, so if we summarize the C++14 lambda, it has come over many obstacles of the C++11. The major one was the capture, that it now captures an expression and we can name that expression. We can capture a variable from the scope with a different name. Another thing is that it has now default parameter value, and then generic lambda. Generic lambda is very good thing in C++14, because if you want, if there is no way, because only C++17, C+20 allow the same kind of thing in for named function, that you can specify auto in the parameter list. And we know that const expr was introduced in C++11, but till this C++11 and 14, lambda cannot be const expr. Now, another problem was still there, that when we capture this, there was no way to capture this by value. C++17 comes over these two obstacles. What it does, that it makes the const expr lambda const expr implicitly, and if that lambda fulfills the requirements of a const expr function, it is implicitly const expr. You can also declare it const expr explicitly, and if it does not fulfill the requirement of const expr, it will result into an compilation error. You can use dereference this to capture this by value. And another thing is that if we have a local variable which is not constant, and if we wanted to capture by constant reference, there was no way. Since C++17, we can do that because there is a standard function called or a library function stdhconst, which allows us to capture by constant. So first, let's see the const expr lambda. So here you can see that I have defined a lambda and I am using static asset, because static asset is evaluated during compile time, and here this static asset will not result into compilation error. This will succeed. So this demonstrates that lambda is being evaluated in the compile time context. So this is implicitly const expr since C++17. So what changes for this const expr thing? That our member function becomes const expr. Here you can see this becomes const expr, and this is also inline. Inline, and since this is a stateless lambda, means nothing is captured. It is compatible with function pointer, which is also const expr. Next is to demonstrate the difference here that I am using a const expr to specify explicitly that this lambda is const expr, and since it fulfills the requirement of a const expr, this static assertion is passed. And here I am using a static variable, and since statics are not allowed inside the const expr function, this fails to compile. This assertion fails because we cannot evaluate it during compile time. It will be evaluated during runtime only. So if you just want to check that whether your lambda fulfills the requirement of being a const expr, you can explicitly specify it as const expr, and if it does not fulfill the requirement, you will get a compilation error. Next is capture this by value. Here in this example, we can see that I have used two lambda. One captures this, one captures this by value, another captures this by pointer. You can see that thread using star this in lambda prints without any garbage value, while another thread prints the garbage value. The reason is that the thread using this, when invoked the lambda, this goes out of scope and thus results in the garbage value. And the one using the this by value has the value inside the lambda and prints the expected result. So what I have done here, let's see. First I have defined a structure, and inside those I have decided the two member function. One is unsafe thread using this, which captures this by value, and it returns this thread which has lambda as executable, and another thread captures this by value, and this also returns the thread. Here I have defined thread T1, defined the object of that type, and called the safe thread, and then joined on that safe thread. In another, the same way, I have joined on unsafe thread, that which captures by value. These two member function returns the thread, and then when I call this, the one using the this by value has no undefined behavior, or you can say the safe behavior. So whenever you are trying to capture anything by reference or by pointer, make sure that that reference or the pointer does not go out of scope. Another thing is that if we use sanitizer in this case, we will see that this will result in an error. This will capture this, that we are trying to access something which goes out of that of the result of the address violation. So sanitizer will be helpful in that case. Next, move to const expr lambda surprise. Since we can use const expr lambda or const expr, we might think that we can use them to access index of any vector or any array. And if we try to do so, we get an error. And that is because the standard says that anything between two consecutive brackets can only be a specifier, like the attribute. Shall one day introduce an attribute, and that is like no discard, all through. If you know these things, may be unused, those attributes. So that's why we cannot use the lambda. This has been reported perhaps as a bug, and maybe will be fixed in later on. So if we want to overcome this obstacle, we can define the lambda, and then we can use the lambda name inside those brackets. And since the lambda is const expr evaluated, this will give us index. As we know that till this time we were only able to give constant inside these indexes. Now if we want to do something like want to use any function to get indexes, we can do here. Another thing that is very surprising in C++7 lambda is that, as we know that C++17 has introduced the structure binding. But if we define the structure binding and try to use those variables inside the lambda, we get error. And this has been fixed in C++20 for according to the standard. It is up to the compiler. Like here in GCC, I am not getting any error with C++17. But if I move to Clang, I will get the error. If I move to C++20, I am still getting the error. But if I move to trunk build, then this has been fixed. So what is the workaround for this? That if we want to come over this obstacle, you just can use init capture. That use x equal to x and y equal to y, and then the problem will be solved, even in C++17. So this is the thing. This has been also reported as bug, and standard fixes it in C++20. So as I have said that in this slide I'm demonstrating two things. First one is that int val, if I want to capture it by reference, there was no way to capture it by constant reference. Now, since the library offers state hconst, I can do this. Here I am not capturing cval, but because this integer is const value, and const integer are implicitly const expr, I can use it without capture. So here I have two lambda 1 and lambda 2. Inside the lambda 1, I'm getting 5, 6, 5, 6 as output. I'm not able to, I will modify this reference. I will get error because this is a constant reference only. And inside 2, if I capture by reference, I will be able to modify this. Since this is by reference, I don't need to use the mutable keyword. So the C++17 lambda has no major features. It has only some utility things, like it has made it const expr. It has given the way to capture this by value, but it does not have introduced any major feature. Till this time, if we want to use the template thing, there is only one way, and that is the generic lambda introduced in C++14. But one of the thing is that if I want to constrain on the parameter list, I want to use it in generic way, but I want to constrain it for a few types. There is no way. Although it is implemented using templated functions, it does not give us to control the type. There is no way that we can control the type of that particular parameter. So the C++1120 lambda has introduced and gives us the ability to introduce the templated function, templated body of the lambda, or you can say templated parameters, and thus gives us the better way to control over our type. So if you want the generic parameter, but we also want to constrain it types or control over it types, we can use the C++20 templated lambda with templated parameter. Another thing that it does is that it deprecates the implicitly capture of this, because this results in undefined behavior. We might forgot or we might not notice that, and so it does this. It has also improvement in capture that we can now simply in C++20 capture the parameter pack. Also, it offers the default constructor for the lambda, means we can now define an object of the lambda using lambda, which calls its default constructor. And it has the advantage that we can use it inside the containers. And another thing is that requires, since C++20 we can use requires, that offers us a better way to control the type of a template parameter. Prior to that, like before C++20, we were using Symfony, and Symfony is not as readable as requires is. Also, you will get a little bit confused when you will write Symfony for the first time. Another thing is new specifier, and that is const eval. So first we see the template lambda. So like we write the normal template function, we can do it here, and it is simply implemented just like the generic lambda of the C++14 using the template parameter. So here we can see it is just a template function. Here I am demonstrating that how I can use type constraints. So here I have taken a team param, return param +1. But as we know that Boolean is also considered as a integer point type. So I can call this lambda using true and false. So I don't want that to happen. I want that to constraint that no one can call this with a Boolean type. So what I can do, that I can write a template function, and then I can write the requires, which allow the integral value and does not allow the Boolean type of. So it allow any kind of integral value, but if it's same as Boolean, it has negotiation. So this constrains the type that now in that case, if I will call lambda with Boolean values like true and false, this will result in compilation error. So this way now template lambda offers us the great way to control the type. Another one is const eval, which is a new specifier introduced in the C++20 lambda what is the difference between const expr and const eval? You can find, you can study, and then you will get the difference. Since const expr and const eval are not compatible with each other, we cannot use those together. Another major change is in C++20 lambda is that lambda are now default constructible. So if you will see on C++ inside, it will have a default constructor for the lambda. Here you can see the lambda has a default constructor. So if I have defined a square to get a square of a number using lambda, I can use decal type L square and then create a default lambda. This will call the default constructor, and I can call this default lambda using this name, this identifier, a default lambda. It will work fine. I can also assign in the same type, the L square, and then call it as it, and it will result in the same thing. So what advantage it has? C++17. Okay, no. So what advantage this default constructor lambda has? I am going to demonstrate using this example. Like if I open it in Compiler Explorer, so here I am using a compare criterion, and I am making a set of this entity, which is a user defined type class person, and I am making a set of this, but I want the comparison criterion to define myself. So I can use this lambda as a compare criterion, and here I am using decal type. Here I am not. Let me see C++17. What was in C++17? In C++17, this will result into error because I need to pass this to the here in the constructor of call, and then it will fulfill the result, because there is no way to call the default constructor of the lambda. If I does not provide it here, this will call this default constructor for this type, and since the lambda before C++20 is not default constructible, this will result into a compilation error. Since C++20 this is default constructible, and now we don't need to provide it as a parameter. Another great thing about C++20 lambda is the lambda in unrelated context. Like we can directly use the lambda inside the decal type and type ID kind of things. And here this will compile fine. This error expected primary expression before auto. Sorry, this one. So now this is giving warning for this one. Okay, we can comment out this. So the C++20 lambda offers that we can use lambda in unrelated context, like in where the lambda is not evaluated, just check for its type, or like in inside the decal type or type ID. Before C++20, there was no way to use that kind of thing. Since C++20, we can do this thing. So inside the decal type, we can directly write the lambda, and by default, it will construct that. Another thing is parameter pack capture. So here we can see that I am using inside a lambda a parameter. I am passing a parameter pack to a template function, and I am capturing this parameter pack inside the lambda here. So C++20 offers the way to capture parameter pack inside the captures. Before C++20, it was not possible. So, and the last one is lambda on heap. And this one is very important. So how we can define the lambda on heap and can use it. So here I have first defined the lambda on heap using raw pointer, new auto, multiplier, just like the lambda, just like we define the raw pointer, I can define it directly here, and then this lambda will become the pointer. I can use dereference it and then call it. If I want to lambda with a smart pointer like here I have done with a unique pointer, we can do in this way. So this way we can define lambda on heap. And with this, the summary is that C++11 introduced the lambda. C++14 has come over the added generalized lambda capture, generic lambda, default parameter value, and variadic lambda. C++17 made it implicitly constructor. It introduced the construct specifier, and it has now one advantage that we can capture this by value. C++20 has the template lambda, default constructible, and assignable of stateless lambda. Const introduced const eval specifier, deprecated implicit capture of this, and it has introduced the stateless lambda in unvalidated context. So this lambda that was here can be used in unvalidated context only if it does not capture anything. So here it was not capturing anything. That's why we were able to use it in unvalidated context, and it has parameter pack capture. Now, two things I have missed in between. I am going to repeat that. Second thing is that first this here in this example, I said that C++20 has deprecated the implicit capture of this. So if I execute in the C++20, this should result in warning implicit capture of this, sorry, here equal to, and this will give us a warning that this capture of this by implicitly by value has been deprecated. And the first thing was this example of using global and local. So all it was about that if we have global and static value or any value which we can use without capturing, and if it is changed in between the captures and the invocation of the lambda, the new value, which is updated value, will be used. If we have captured by reference the local value, then the updated local value will be used. So with this, we talk. Thanks for the talks. Now it's over, and we can discuss if